I'm all about shifting left these days. My designs have gotten more and more complicated, and frankly, I'm tired of getting all the way to the end of a project, bags are packed for Maui, airline tickets purchased, Mai Tai practically in my hand, and finding out that there was a problem way back at the beginning that requires me to practically start all over again. Aloha! With board design, that means I need some industrial strength design rule checking that will keep things in order as I go along with my PCB design, instead of me finding out at the very last minute that something isn't right. Hi, I'm Amelia Dalton, host of Chalk Talk. If you're buying non-refundable vacation tickets, yeah, you'll want to pay attention to this episode, where my guest is Rory Riggs from Mentor, and we're going to talk about Hyperlynx DRC. And third row aisle seat? Yep, booking that now. And before we get started, don't forget to click that link. There you can find more information about Hyperlynx DRC from Mentor. Hi, Rory. Thank you so much for joining me.
Thanks for having me here.
Okay, so what are some of the common problems that PCB designers are facing today? What kind of challenges are you seeing in particular?
I would say extreme design complexity is becoming a growing industry problem for PCB designers. Not only are we innovating and creating more often, but we're creating way more complex designs. Some examples, Mentor customers who are facing this problem in creating a binocular helmet-mounted display, they faced extreme design complexity in that they had 2,300 plus parts on this design and over 12,000 vias and 30 plus different voltage rails. So we're talking an extremely complex PCB. Same thing with this one, had a PCB with 5,000 plus parts and 31,000 connections. So you can imagine just how complex their designs are.
Absolutely. So, Rory, these seem like unique cases, but what are some more common problems here?
I'd say that there are many different standard protocols that exist on PCBs today. We're talking about USB 3.0, 3.1 protocols. These exist on almost every PCB. PCI Express, Gen 2, Gen 3, Gen 4, DDR, DDR2, DDR3, DDR4, soon to be DDR5. As these trends and standards become more readily adopted, they exist everywhere. And the hardware engineer has a very unique challenge here in that they have to acquire the knowledge to make these protocols pass every time.
Sure.
On their PCBs. They don't have the signal integrity or EMI expertise to validate these protocols. In DDR, for example, they have to go out and acquire this knowledge. They have to redesign guidelines. They have to read data sheets. Some of these app notes, one I was using for the PCB we're using in the demo today, it was a 206-page app note from an IC vendor.
Wow.
So just understanding the knowledge that goes into one of these can take a lot of time and experience.
Sure. So I don't know about the team you work with, but most designers I know, they don't want to learn a new tool to help them get the job done.
Oh, yeah, I completely agree with that. Ideally, the tool that the PCB engineer adopts should be easy to use and not something that they have to learn on their own when they're trying to go out and acquire this knowledge to solve the problem. They don't want to have to go out and learn a new tool and invest that time.
Yeah.
What we're seeing with PCB designers is that the tools are not only complex and incomplete, but if they're not part of the same flow. For instance, if you have a schematic tool from one vendor and a layout tool from Mentor and a simulation tool from one of our competitors, these tools don't all fluidly talk to each other and they don't work together well because they're all part of different companies. And so what we're seeing is that domain experts who should be solving these problems and finding the inherent cause of the problem, they're tied up in learning new tools. They're tied up in manually and tediously inspecting each board layer by layer, net by net. And what we want to achieve here with Mentor customers is to provide a solution that finds these and automates these tedious problems and frees up the experts' time so that they can solve the problems that they're paid to solve.
Excellent. All right, Rory, it's time to talk about the elephant in the room, respins.
Yeah, so I ask this question a lot every time I give a talk. I did a whole roadshow this year called PCB Forums through Mentor. We did a survey with Aberdeen, and they found that 78% of all projects experience 2 or more respins. And I asked this to the audience in Chicago, and someone in the room said that number should be 99% because they always experience it. So we're finding that as the PCBs become more complex, they become smaller, they become more complicated. We talked about all the adopting of all the standard protocols now that exist. As these problems become more challenging to solve, we're seeing more respins with our customers.
All right. Now, how many hours and days are we really talking about, Rory? And we're not just talking about bugs, right? We're talking about human error here as well.
Yeah, so typically, if this depends on the PCB. If you have a simple PCB, not a lot of high-speed signals on it, you don't have DDR4 or something like this, then validating that PCB could take a day.
Okay.
But on some of these more complex problems, we're talking creepage and high voltage issues, safety issues, PCIe, SerDes nets. We're talking high-speed signals, 20 gigs plus signals. Validating these high-speed critical nets can take hours, days, or longer. Even a whole team of engineers can be deployed trying to find these problems.
Yeah.
And the big challenge here also is that who can find these problems? Who can check? And can every PCB designer find every signal integrity, every power integrity, every EMI issue?
Right.
And if they can't, then they have to go acquire this knowledge to find and solve these problems, or talk to somebody who can, and their time can become limited. And if you're always checking for these problems manually with your visual, own eyes, peer inspection, humans have the tendency to miss a problem, or maybe not be as accurate as a geometric algorithmic tool can be.
Sure.
So Hyperlynx DRC is a Mentor Graphics solution to finding these problems. So the benefits of using Hyperlynx DRC is that it can find these tedious errors in seconds or minutes, can be deployed in an unlimited amount. It won't get tired. It won't need coffee. It'll find these, it'll find the issues accurately. And not only is it accurate, but it's informative because it's explaining what it's looking for. It's showing the PCB designer, this is why I'm checking for this. This is the problem, and this is why we're checking. So it's also kind of a learning tool as well. You can deploy it to anybody at your company, or anyone can use it. So it's very, very easy to use and very easy to deploy and reuse prototype to prototype with PCBs.
Okay, so how does this compare with a more traditional design process?
So the conventional design process is, so for a PCB design flow, we have the schematic stage where we design the schematic, do all the front end schematic authoring, and then we'll move into the layout stage. We'll do the placement of the components. We'll route the critical nets, finalize the PCB with manufacturing, and then typically designers will check for problems before they go to the prototyping stage or the final product stage. And this is if they have time to do a check.
Right.
Most often, you'll find, just talking with designers, that they don't have time to check, or they only have time to check the critical nets. I don't have time to check every net in the design. I can't check, layer by layer, but I'll check these critical power areas or power circuits of my board, but I won't check every circuit. So what Mentor Graphics is proposing is a left shift methodology with its tools. We are bringing the simulation, we're bringing the checks and the validation and the verification to each stage of the design cycle. So if you're in the layout stage, for instance, with Hyperlynx DRC, it can automatically check for all the layout problems that you would have to do manually. And then the person who's most equipped to fix that problem, the hardware engineer, the PCB designer, the layout expert, they're finding the problem during design.
Nice.
So then they can fix it immediately. They don't have to, let's say you signed off on the layout in July, and then you passed it to manufacturing in August, and then in September, they did the reliability check.
Yeah.
And they found a layout problem. Well, then guess what? 2 months ago, you thought you were done with that, and then they bring it back to you, and you got to move a net, or you got to add copper here, or you got to rework this placement. But if you found those problems immediately, you wouldn't have to waste all that time. It would be very useful that the expert who's fixing it is the one finding it.
Absolutely. Okay, Rory, so what exactly is Hyperlynx DRC? Is this the same as a standard layout DRC?
So no, Hyperlynx DRC is different than a layout DRC. It's an electrical-based rule-checking tool. So it goes hand in hand with the layout DRC, actually.
Okay.
It doesn't replace the layout DRC, it enhances it. So Hyperlynx DRC, in its simplest explanation, it's just an automated electrical rule-based design checking tool.
Okay.
So it removes the need for the manual peer inspection. The layout designer would have to go layer by layer, net by net, checking for signal integrity issues, power integrity issues, electromagnetic interference issues. So what Hyperlynx DRC, by doing this automatically, it reduces that cycle time, verifying time, to minutes and hours. And it allows not for just one check at the end of the design cycle, it allows for many checks, throughout the layout. You could run Hyperlynx DRC every night when you went home after work, go in the morning and look at the layout again, and you would have run a simulation. Now, how often can you say that you run simulations every day or you run checks every day?
No.
So not only that, it's very easy to use. There's a lot of out-of-the-box rules, but it also allows for the customization of your own checks. So a lot of current Mentor customers using Hyperlynx DRC have their own customized rule decks. And you can write your own rules. Mentor can write the rules for you, and we can teach you this process as well. So the tool has its own script writing and debugging environment.
Cool. Okay. So what kind of out-of-the-box checks are we looking at here? The ones that layout won't check for?
Yeah. So currently, every release, we add more DRCs to Hyperlynx DRC.
Okay.
But right now, there's a little over 40 built-in rules. They're broken down into 3 different categories. We have the examples being for EMI checks. We'll check for nets crossing gaps and split planes. So this is a common issue that is very tedious to find. So if a high-speed signal or trace crosses a gap in a split plane, which is very common, you'll see an impedance change, and that'll cause a reflection of that signal. So the solution here is to add more copper, add a stitching component, or move the net. You don't want to be moving nets or moving components around after you've already finalized your layout or after you're already into manufacturing, right? So you want to catch these problems up front. And the way you catch those problems typically is to manually check every high-speed net, look at every single one, layer by layer, net by net.
Right.
So this is one of the EMI examples built in out of the box. It's very simple, but it does it automatically for the user. There are signal integrity checks as well, like crosstalk examples and differential and single-ended net impedance checks, termination checks. And for power integrity, there's decoupling capacitor proximity checks, making sure that your decoupling capacitors are as close as they need to be to the IC power pins to be effective, and just other built-in power integrity checks that we'll go into.
Cool, okay.
So a full list of the DRCs are shown here. The standard DRCs, this was the first iteration of Hyperlynx DRC a few years ago. We really needed to beef up that power integrity category, so every release we've added more rules. And the ones that we're really excited about with the VX 2.2 and 2.3 updates are the new creepage and clearance rules, which I'll go into later.
All right, so let's get into hyperlinks here, Rory.
So what you're looking at here, I kind of like showing a little preview of what the tool is going to look like before we just jump right into a demo, so that anyone who's not seen the tool is aware of where everything's located. Mentor PCB tools are all pretty standard. On the top left, we'll have that Project Explorer, and this is where we're going to see all the out-of-the-box rules and all their rule category folders, and you can customize this if you want.
Cool, okay.
And this is where all the layout information is imported. So Hyperlynx DRC will check any layout, not just Mentor's Expedition or Mentor pads. So it will check any layout flow. It'll check Zukin data, Cadence data, OWB++, all the layouts.
Cool, okay.
This is where you're going to see all that information being imported automatically. There in the bottom that we have boxed in red are the parameters and the violations. This is the output window. This is where you're going to see where the errors are occurring.
Okay.
And where you're going to put in the datasheet information or the design guideline information for checking for your protocol. And then the main window will have the overview explanation. So this is where if we click on a rule, everything's context sensitive. So anytime you click anywhere in Hyperlynx DRC, your properties window will update, your spreadsheet will update, and the main overview window will update as well, and it'll explain the purpose of the rule, why we're checking for it, what it's actually doing. It gives you a little overview and explanation of why we need to care about that kind of issue.
Excellent. Rory, let's see this in action.
So here in the Project Explorer, like I said earlier, this is where all the layout information is imported automatically. You'll have all the electrical nets, all the layer information, the net classes, the constraints, they all come over automatically. So you don't have to set this up beforehand or anything. Hyperlynx DRC will be able to read your layout. And then the analysis setup, this is where we have the more system-generated object lists. So the object lists are how we're going to target portions of our PCB. And every PCB is different, so these are a necessity. You have the ability to create your own user object lists as well. Like you'll see that I made some DDR401s and some PCIe object lists for this particular PCB that has a DDR4 on it. And then we'll have all the out-of-the-box rules. We have the EMI. We'll start here, and we'll pick a couple EMI out-of-the-box rules to run and execute. So it's as simple as right-clicking on the rule and hitting execute or hitting run. Hyperlynx DRC will check for these problems that you would have to find manually. So what we're looking at here is the net near plane edge. So here we're looking at nets that come near a plane edge, a plane shape, or the edge of the board. This is something that has to be done and checked for manually. And if you just click on the violation in the spreadsheet window, Hyperlynx DRC will automatically snap to the violation where it occurs. It'll highlight it in red. In the bottom right, you'll get some details on why it's a problem and advice on how to fix it. And it's just very simple to find these problems. You just click on a violation, and then Hyperlynx DRC changes the layer information for you and just shows you immediately. Another check is Metal Island, which finds isolated copper. This is an EMI issue that's common to find. And then there's that net crossing gaps rule that I talked about earlier, where we're finding nets that cross gaps in split planes. And to find these nets would be very tedious. You'd have to look at every net in the design. You'd have to find these gaps in split planes. And then you'd have to move the nets or add copper or add a stitching component. So Hyperlynx DRC will do that for you. For a power integrity example, out of the box, we have a decoupling capacitor replacement rule. Like I said earlier, this will check for IC power pins and decoupling capacitors and making sure the proper voltage is there to decouple that IC power pin. To do this manually, you'd have to search and look at all your critical ICs and try to find, or if your nearby capacitors are in range. Hyperlynx DRC shows that bubble, the radius that it's searching for, and saying, oh, I can't find any caps here. I need them, to be closer. Or the caps that are in place are not the proper ones to decouple. For the signal integrity, we have a lot of examples. Right here, we're doing a breakout and trace integrity. So this is just checking the neck down length on a package IC pin. And clicking on the violation, we'll see, oh, we were looking for 100 mils required maximum for this neck down length. And really, it's 143.6. So it found it automatically. You saw it took a couple of seconds. It was very, very simple to run and execute. And here I want to pause and switch gears a little bit. So like I said, Hyperlynx DRC can work in any layout flow. It'll check every layout, not just Mentor. But the benefits of being on a Mentor flow and using Expedition, for example, is that these DRCs can be used directly inside of Expedition as well. So we have the standalone version and then the integrated version. So here I want to unpause and show you how Hyperlynx DRC works inside of Expedition. So here we're actually in the layout tool. So if we're the PCB designer and this is the tool that we're used to using, we don't have to learn a new tool. We just open a new GUI menu called the analysis control and then start the Hyperlynx DRC client. So we're not learning and not investing time in learning a whole new complex tool. We're using the layout tool that we're already used to using. We're going to run those same checks we just ran, one of the power integrity checks, the net near the plane edge, and then the breakout and trace integrity check. And then we just click Analyze Design. And since we're in Expedition now, we don't report violations via the spreadsheet like we did in Hyperlynx DRC. Expedition GUIs use the Hazard Explorer, so it's something that you're already used to using if you're using the Mentor tools. And as we open the Hazard Explorer, you'll see a Hyperlynx DRC tab now. And it's the same functionality that the standalone tool uses. You click on the violation, it'll switch the layer scheme, the display for you. It'll highlight in red where the error is. And then now, since we're already in the layout and we're the PCB designer, we can actually make those design changes immediately. We're in the layout tool where there's no exporting and importing of data back and forth. We're reading all our constraints automatically because we're using the constraints from the layout tool inside the layout tool. And you can see how easy it is for the designer to catch these problems up front and then make these changes immediately.
All right, Rory, pop quiz time. What do you think is the most tedious issue, the biggest headache for manually checking that engineers are facing today?
I would have to say the biggest headache that engineers face are the creepage high voltage safety issues. Not every designer faces this. This is more common in household application circuits where we're using high voltage in the public sector, and in the private sector with the mil-aero engineers, they have to deal with high voltage, safety issues, and tight enclosed spaces. So this creepage problem is very, very tedious to check for. So what happens here if you are unfamiliar with creepage and clearance, the difference between the creepage distance and the clearance distance is that the creepage distance will mind an air gap.
Okay.
So clearance distance is just the shortest path between two objects. The creepage distance is the shortest distance along the surface of an insulating material between the two conductive parts. But the real problem here is not that it's hard to calculate for, because it's a simple ratio depending on the scenario. It's just the creepage distance is simply 1/3 of the clearance length. Depending on the situation, though, this can change.
Ah, okay.
And so if we have a floating metal object, which is common in every PCB, we have other nets and other objects. Depending on the material of that floating metal in between, you can treat the floating metal as an extension of the high voltage net or an extension of the victim net, the low voltage net.
Okay.
And so the creepage distance becomes an extremely difficult problem when you look at it in that perspective, because how the process is today is that the designer will manually check for these nets. They'll manually check all the high voltage nets and see if they're creeping to victim nets. And then they have to look up in a chart, a national standard or an IEC international standard chart. They have to look up the material group for the floating metal.
Okay.
And then they have to know the pollution degree of the environment that they're in. And yeah, it's, it's a 1/3 clearance distance plus this, or depending on this, you need to know this material, though depending on this, it's this factor. Depending on this voltage, it's this in the chart. So yes, it's very simple to calculate, but very, very tedious and very, very time consuming.
Sounds like it.
There's no tool that exists today that can do this automatically. But Hyperlynx DRC, we've customized some new creepage and clearance rules to approach this problem to solve it automatically for the user. So here I want to show 2 iterations of our new creepage and clearance rules. So the first rule we're going to look at is a simple 2D creepage rule. So we're talking same layer, high voltage net to low voltage net, same layer. Very simple rule, just checking for creepage distance only.
Okay.
So we're not looking at any floating metal in between. We're not using the material group right now. We're not using the pollution degree of the environment. We're just looking at creepage distance purely. So running the rule in Hyperlynx DRC, they take a little longer because there's more to check for here. They're not as quick as the other rules. But if you look at it in terms of time saved with the calculations, looking up the charts and all that, you save a lot of time. So what we're looking at here with violation 7 and 8 is that we just have green being the victim net, and in the dark tan is the high voltage aggressor net, and you'll see that there's a mounting hole. So that blue line is the creepage distance calculation, and it's minding that air gap. It knows it needs to walk around this. It's not, the clearance distance would be the shortest path over that gap. Creepage distance is the keeping that gap in mind. And with that, we'll pause for a second and we'll talk about the actual real creepage for safety standards rule that Mentor has written. So this rule will check for, we're going to do the same example. We'll do the same layer. And this will keep into account now the pollution degree of the environment, the material group of any floating metal. And what you'll see is that the rule will actually find where if we were just doing a simple creepage check, it would be a rudimentary just distance, right?
Right.
But because of all these other elements in the design, which are very common, other nets, other components, you'll see that there's no way you could do this manually.
Sure, yeah.
So we'll hit play again, and we'll run through all this. So here we have the purpose of the rule, which we just set up. In the parameters window, we can change, click in any of these boxes, and depending on our pollution degree, this is what we're going to get from our charts. This is how we're going to use data sheets. Here's an example of one of these charts. We have the voltage on the left. For our example, it's a 100 volt aggressor. So we need to look at that column, material group 2, pollution degree 2. This is the chart that everyone will use. So Hyperlynx DRC has these charts built into the rule.
Nice.
You no longer have to look these up on your own, have it in front of you on your desk. The rule is using these charts ingrained. And after running the rule and finding a violation, we'll see the creepage distance. So here, if you look at it, it looks very simple. It's in the bottom right, in the details, you can see the creepage distance is 15 mils, but the required distance was 19.7. But zooming out, you'll see how complex this actually was to get to that creepage distance point. So here on the bottom right of the board, I'm going to zoom in. And you can see in lime green, that's the actual victim net. Now, the dark green are the nearby floating metals that can be assumed to also be the victim net. And then if you look at the distance between the actual victim net and the high voltage aggressor, it's 513 mils. So this wouldn't have flagged if you were just looking for creepage distance.
Yeah.
But because we're in a high voltage environment, we have to care about the international standards. We need to know about the floating metals nearby. We need to know about the pollution degree of our environment. In reality, if you move to the left of the board, you see this high voltage aggressor on the bottom is actually creeping to all these other tan nets. And these all can be considered an extension of the high voltage net. So the actual creepage distance, between those two nets wasn't 500 mils, it's 15. But to find that manually, you have to go net by net, and you saw how many, we're talking 100 plus nets here on each side.
Yeah.
To find this manually, okay, let's check this net. Is that one a floating metal? Yes, it is. Look it up in the chart. Okay, is it within 1/3 of the distance of clearance distance? It is. Okay, that's a creepage net. That's a high voltage net now. And then you move on to the next one. You move on to the next one. You move on to the next one. And what Hyperlynx DRC found in about a minute of execution time would have taken, days for engineers. How tedious would that be to go in there and manually look at this?
Right.
And here, if you look at the violation conditions of the rule, this is all built into the rule. All of this is automated for the user. We're not replacing the engineers who have to check for this problem. We're making their lives a lot easier. This is a tool in their tool belt to find this problem, and then they can go fix it. They can go move the nets, or they can go correct that safety violation.
Excellent. Well, before we go, Rory, can you recap your main points for me?
Yeah, Hyperlynx DRC is an electrical-based rule-checking tool that's used for automatically verifying any PCB layout. So it'll replace all that tedious manual inspection that PCB designers face today. Deploying Hyperlynx DRC is very easy to do. It allows anybody to run checks on signal integrity and power integrity and EMI issues. You don't have to be an expert to run these checks, but it will prevent those design respins that you manually check for today. And if you are unsure about it or want to try it for yourself and just see it with your own eyes, there's a free version available on mentor.com with 8 of the 40 out-of-the-box rules currently available for free.
Excellent. Well, I think that's all I have time for today. Thank you so much for joining me, Rory.
Thank you.
And before we go, you didn't forget to click that link, did you? There you can find more information about Hyperlynx DRC from Mentor. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out the Chalk Talk section of EE Journal or head on over to YouTube. Keyword EE Journal.